Ancient engineers built machines that defy modern replication. We will explore the 24 most mysterious devices from the ancient world, inventions so advanced they challenge everything we think we know about historical technology. You will discover how civilizations without computers or electricity created precision astronomical calculators, unbreakable metals, and weapons that harnessed the elements. What secrets did they know that we have since forgotten? How did they achieve such brilliance with simple tools? By the end, you will see history not as a linear progression, but as a story filled with peaks of genius that vanished into time. What does it truly mean to call something advanced? These ancient wonders did not emerge from a vacuum. They were born from specific needs, driven by the relentless human spirit to solve problems, to understand the universe, and to leave a lasting mark. To truly grasp the genius behind a 2,000-year-old astronomical computer or an unbreakable sword, we must first step into the world of its creators. We must consider the materials they had at hand: simple bronze and iron, wood and stone. We must appreciate the scientific understanding they painstakingly built through observation alone, without the tools we take for granted. And we must recognize the powerful motivations that fueled such innovation, whether it was the desire to predict the seasons for planting, to gain an advantage in warfare, or to honor the gods with magnificent temples and rituals. This rich tapestry of necessity, knowledge, and belief is the true foundation for every impossible machine we are about to uncover. Buried in the silent darkness of a shipwreck for 2,000 years, the Antikythera Mechanism was a secret the sea nearly kept forever. Sponge divers discovered it off the coast of a tiny Greek island in 1901, but it was just a lump of corroded bronze and wood, seemingly worthless next to the statues and coins recovered from the same wreck. For decades, it sat in a museum, a forgotten curiosity. Then, researchers began to look closer. X-rays and advanced imaging revealed the truth. This was not a simple statue fragment. It was a machine, an impossibly complex clockwork device of at least 30 precise interlocking bronze gears, all housed in a wooden case no larger than a shoebox. Inscriptions on its face acted as a detailed user manual, explaining the celestial dance it was built to calculate. This was without doubt the world's first known analog computer. Built around 100 years before the Common Era, its purpose was to model the universe. By turning a hand crank on its side, an ancient user could advance the mechanism through time. On the front, dials would show the positions of the sun, the moon, and the planets against the backdrop of the Egyptian zodiac. Another dial could predict lunar and solar eclipses with stunning accuracy. On the back, two spiral dials acted as a calendar, tracking the 4-year cycle of the ancient Olympic Games and other important civic events. This was not a toy for the wealthy. It was a sophisticated scientific instrument, likely used for navigation, for setting religious festivals, and for understanding the orderly, mechanical nature of the cosmos as the Greeks saw it. The true mystery lies in its engineering. The gear teeth were cut with a precision we would not see again until the Industrial Revolution. One gear even has 223 teeth, a number directly tied to the Saros cycle, a periodicity of eclipses. This was not guesswork. This was applied, intricate mathematical knowledge forged into metal. Who designed this? We have no names, no blueprints. The lone surviving device suggests it was not unique, that this level of technology existed. And then the knowledge vanished. For over 1,000 years, nothing of its mechanical sophistication would appear again in the historical record. How did they achieve such precision without modern tools, and why was this brilliant technology lost to the ages? The answer may lie not in the stars, but in another ancient wonder forged in fire and legend. While the Antikythera Mechanism was a complex machine of known genius, other ancient objects are confounding precisely because their purpose is a total enigma. Scattered across the former expanse of the Roman Empire, from Wales to Hungary, are dozens of strange, fist-sized bronze artifacts that defy categorization. Each one is a hollow, 12-sided geometric form, a dodecahedron with a circular hole cut perfectly in the center of every pentagonal face. The holes are all different sizes. They are exquisitely crafted, often with small knobs at each corner where the faces meet. Ranging from about 4 to 11 centimeters across, they show no signs of wear or damage, no inscriptions, and no accompanying instructions. They simply appear in the archaeological record, perfectly preserved and utterly silent about their function. The uniformity of their design is a clear signal. This was not a folk art project or a one-off oddity. These objects were made to a standardized pattern, implying a common, widely understood purpose across the vast Roman world. Yet that common knowledge has been completely erased by time. The theories about their use are as varied as they are inventive. Some suggest they were sophisticated tools for astronomical observation, perhaps used by surveyors to calculate distances or to determine the optimal planting dates by gauging the angle of sunlight through the different holes. Others propose they were practical devices for knitting gloves, a theory that persists despite a lack of any evidence of thread wear on the bronze. More speculative ideas cast them as religious relics, ceremonial standards for military units, or even toys. But every idea collapses under scrutiny. If they were measuring devices, why are they not found with any other surveying tools? If they were for knitting, why are they made from valuable bronze and not wood? Their perfect preservation suggests they were not everyday tools subjected to hard labor. They feel special, perhaps even sacred. This is the core of their mystery. They are not grand monuments or lost technologies of obvious power. They are small, personal, and beautifully made objects that were clearly important enough to be crafted with care and carried across an empire. They represent a complete disconnect in our understanding. We can decipher the inner workings of a 2,000-year-old analog computer, but we cannot figure out what a common, hole-ridden bronze object was for. It is a humbling reminder that the past is not just a collection of grand inventions and known histories. It is also filled with the quiet, everyday secrets of people whose world and whose common sense we can only guess at. What other simple objects from our own time will future archaeologists unearth, holding them in their hands and wondering what on earth we used them for? This puzzle of a simple shape leads us to another, far more imposing Roman mystery, one carved not from metal but from stone. While the Romans left us a silent geometric puzzle, another ancient culture may have left behind something even more astonishing. A device that seems to hum with a power we thought was discovered millennia later. In the basement of the National Museum of Iraq in Baghdad sits a simple, unassuming clay pot, roughly the size of a man's fist. It dates back to the Parthian period, around 250 years before the Common Era. Found alongside other mundane artifacts in a village near the city, it would have been easy to overlook. But this was no ordinary pot. Inside the 13-centimeter-tall clay jar, researchers found a sealed copper cylinder, and within that, an iron rod. The jar showed signs of corrosion, as if it had once held an acidic liquid like vinegar or wine. To the eyes of German archaeologist Wilhelm Koenig in 1938, it looked eerily familiar. He proposed a theory so radical it was immediately dismissed by many. This object, he claimed, was an ancient electric battery. The principle is simple yet brilliant. If you fill the jar with an acidic electrolyte, a chemical reaction occurs. The acidic liquid acts on the two different metals, the iron rod and the copper tube. This creates a potential difference, a voltage between them. If you were to connect the copper and the iron with a wire, a small electric current would flow, about 1 or 2 volts, enough to generate a slight tingle or a very faint spark. Replicas built based on this design have proven it works. The question is not could it generate electricity, but did the ancient Parthians intend for it to do so? What possible use could they have had for a trickle of electric current 2,000 years ago? The most compelling theory is electroplating, the process of using electricity to coat a common metal like copper with a thin layer of a precious metal like gold. This technique was known in the region, and a series of these batteries linked together could have provided enough power for such a delicate task. Other, more speculative ideas suggest the current could have been used for medical purposes, a form of ancient electrotherapy to treat pain, or even for religious ceremonies, perhaps to produce a mysterious tingling sensation from a statue to astonish worshippers. Yet, like the Roman Dodecahedron, conclusive proof is maddeningly absent. No wires have been found with them, no texts describe their operation. They remain isolated, enigmatic objects. Their very existence forces a profound question. Was this a forgotten technology, a happy accident, or merely a storage jar for sacred scrolls, with the metal components being nothing more than a protective case? The fact that it works at all is what makes it so deeply compelling. It challenges the very timeline of human invention, suggesting that the spark of discovery can flicker into life in any era, only to be snuffed out by time, waiting to be rediscovered centuries later. This notion of a lost science, of knowledge that appears and then vanishes without a trace, finds its ultimate expression in a material that seems to defy the very laws of nature itself. But the most legendary flame of the ancient world was not a natural phenomenon. It was a weapon. Across the centuries, from the dark waters of the Bosporus to the walls of Constantinople itself, a terrifying specter haunted the enemies of the Byzantine Empire. It was a fire that water could not quench, a liquid hell that clung to wooden hulls and the flesh of sailors, burning with a fury that seemed almost supernatural. This was Greek fire, and the machine that unleashed it was the most closely guarded state secret of its age. The exact formula for the incendiary mixture was known only to a select few, possibly even only to the emperor and one family of chemists. Its composition died with them. Based on contemporary accounts, we believe it was a volatile cocktail of crude petroleum drawn from natural wells around the Black Sea, mixed with powdered quicklime, which ignites upon contact with water, and potentially other resins or chemicals like sulfur or saltpeter. This created a sticky, napalm-like substance that not only burned fiercely but was nearly impossible to extinguish, as dousing it with water only intensified the flames. The true genius, however, lay not just in the chemical recipe but in its deployment. This was not simply flung in pots. The Byzantines engineered a sophisticated projector, a pressurized nozzle system often mounted on the prows of their warships or the walls of their city. Some accounts describe a bronze tube connected to a large reservoir and a pump, operated by a crew who would heat the mixture before unleashing it with a terrifying roar. The operator would aim this primitive flamethrower, spraying a continuous jet of liquid fire across the water to engulf enemy vessels. The psychological impact was as devastating as the physical damage. Imagine facing a fleet that could command fire itself, a weapon so terrifying it could turn the tide of a naval battle in an instant and secure an empire for centuries. Its loss represents one of history's most stark technological regressions. How did they achieve such precise chemical engineering without the foundational knowledge of modern science? They understood the reactive properties of their ingredients through sheer, painstaking experimentation. They mastered pressure and mechanics to create a delivery system that was both effective and survivable for the operator. This was not magic. It was applied science of the highest order, a deadly art that was protected so fiercely it was ultimately lost. The secret of Greek fire vanished, leaving behind only echoes of its terrifying power in the accounts of those who witnessed it, and a question that still smolders. What other formulas, what other machines of war or peace have been lost because their secrets were too closely held? This pursuit of the ultimate weapon leads us from the burning sea to a different kind of arms race, one fought not with chemistry, but with the impossible strength of a forgotten metal. Yet for all its destructive power, Greek fire was a triumph of chemistry, not mechanics. For a true glimpse of lost mechanical genius, we must turn from the chaos of the battlefield to the quiet contemplation of a scholar's workshop. In the 1st century of the Common Era, in the great library of Alexandria, an inventor named Hero demonstrated a principle that would one day power the entire modern world. He called it an Aeolipile. At first glance, it seems like a simple curiosity, a beautiful toy. A hollow metal sphere is mounted on a boiler. 2 pipes connect them, and from the sphere, 2 more pipes curve outward like arms, each ending in a narrow nozzle pointed in opposite directions. The boiler is heated, and water within it begins to boil. Steam rushes up through the pipes into the sphere, building pressure with nowhere to go except out through the 2 small nozzles. As the steam jets out, it creates thrust, a reactive force, and just like a rocket, the sphere begins to spin. Faster and faster it rotates, a whirling metal ball powered by nothing but steam, a miniature engine humming with potential. This was no mere parlor trick. Hero had not only conceived of steam power, he had built a working model that demonstrated the fundamental principle of action and reaction, a concept Isaac Newton would formally define more than 1600 years later. The Aeolipile is without any doubt the first recorded steam engine in history, and that fact is the very heart of its profound mystery. It worked, the science was sound. The materials were available, the knowledge existed, so why did this brilliant invention remain nothing more than a fascinating demonstration? Why did it not lead to steam-powered pumps for mines, or looms for factories, or ships to cross oceans? Why did the ancient world not launch its own industrial revolution? The answer is as complex as it is frustrating. Hero's world, for all its intellectual achievements, lacked a critical economic driver. Labor was cheap and plentiful, often supplied by slaves. There was no pressing need to develop machines to replace human muscle on a massive scale. The Aeolipile was seen as a wonder, a marvel to illustrate a philosophical point about the power of air, not as a practical tool to solve a problem. It was a solution in search of a problem that ancient society did not know it had. The mechanical knowledge was there, but the necessity, the economic incentive, was absent. This gap between invention and application is one of the most haunting aspects of technological history. It forces us to ask what truly drives progress. Is it simply the spark of a brilliant idea, or is it the specific conditions of a society that is ready, even desperate, to use it? The Aeolipile spins in its lonely glory, a ghost of a future that arrived 18 centuries too late, a poignant reminder that genius alone is not enough. It must land on fertile ground, and sometimes the most advanced machines are not made of metal and steam, but of something far more enigmatic and enduring. While Hero's steam engine remained a beautiful thought experiment, another ancient invention served a purpose so vital its success was recorded for history. In the year 138 of the Common Era, A bronze dragon on an ornate vessel in the Chinese capital suddenly spat a heavy bronze ball. It clattered into the waiting mouth of a metal frog below, pointing decisively towards the west. To the court officials in Luoyang, the city felt still and calm. There was no tremble in the ground, no sign of any disturbance. Many dismissed the device as a failure, but days later, a messenger arrived from the western frontier, exhausted and covered in dust. He reported a devastating earthquake had struck a province hundreds of miles away. At the exact moment the dragon had released its ball, the machine had been right. This was the Seismoscope of Zhang Heng, a brilliant astronomer, cartographer, and engineer of the Han Dynasty. His device was a masterpiece of both art and hidden science. A large urn-shaped vessel of fine bronze was decorated with 8 dragons snaking down its sides, each one poised above a corresponding frog with its mouth wide open. Inside this vessel was the true mystery, a mechanism so clever its secret died with its inventor. The most plausible theory suggests a heavy pendulum was suspended in the center of the urn. At the slightest tremor from a distant quake, the delicate inertia of the pendulum would be disturbed. It would swing, even just a little, and strike a lever mechanism connected to one of the 8 dragons. This would release the ball clasped in that dragon's jaw, providing a clear and undeniable direction to the origin of the seismic waves. Think of the precision required. The mechanism had to be sensitive enough to react to vibrations traveling hundreds of miles through the earth, yet stable enough to ignore the rumble of a passing cart or the footsteps of a crowd just outside the palace. How did Zhang Heng calibrate such a device without ever experiencing a controlled earthquake? He must have possessed a deep, intuitive understanding of wave mechanics and resonance, principles we would not formally define for nearly 2,000 years. His invention was not just a detector, it was an early warning system. By knowing the direction of a quake, the imperial court could dispatch aid and investigate damage long before word could travel by horse or foot, saving countless lives. The fact that its internal workings remain a subject of debate today is a testament to its sophistication. Zhang Heng built a machine that could feel the heartbeat of the planet itself, and then he took the secret of how it worked to his grave. This pursuit of measuring the immeasurable leads us from the solid earth to the empty sky, and another instrument that mapped the heavens with impossible accuracy. Archimedes, the legendary mind behind levers and buoyancy, is also credited with a weapon that sounds like it was stolen from a science fiction story. As the Roman fleet bore down on his home city of Syracuse, the story goes that the elderly inventor devised a desperate and brilliant defense. He instructed soldiers to polish their bronze shields to a mirror-like finish. They then arranged these shields in a vast, precise parabola, each one angled to catch the sun's rays and reflect them towards a single, focused point on the wooden hulls of the approaching warships. According to the ancient accounts, it worked. A beam of concentrated solar energy harnessed from the very sky struck the ships, smoke began to rise, and then flames erupted. The Roman fleet, threatened by an invisible force they could not fight, was thrown into panic and retreat. This is the legend of the Archimedes Heat Ray, a device that turned sunlight into a siege weapon. But did it actually happen? Modern attempts to recreate this feat have been notoriously inconclusive. A team from the Massachusetts Institute of Technology conducted a famous experiment in 2005. Using a large array of mirrors, they managed to set a wooden mock-up of a ship on fire, but only under ideal, stationary conditions with a perfectly clear sky. Other attempts have failed entirely, generating heat but never a sustainable flame. The skeptics argue that the technology of the time could not have produced mirrors with the necessary reflectivity, or the precise alignment required to maintain a focal point on a moving, rocking ship at sea. The logistics of coordinating hundreds of soldiers holding heavy shields steady seem nearly impossible, yet the story persists, and for a compelling reason. The fundamental science is absolutely sound. We use the principle of concentrated solar energy every day. The concept is not the mystery. The feasibility on a battlefield scale is what we debate. Perhaps the true genius of Archimedes was not in the literal construction of a death ray, but in the application of profound optical theory to warfare. He understood the properties of light and reflection better than anyone in the ancient world. Maybe he devised a system that used fewer, larger mirrors mounted on the city walls, creating a terrifying glare and intense heat that, while perhaps not instantly incendiary, could have scorched sails, blinded crews, and created enough confusion and psychological terror to be an effective deterrent. The legend endures because it celebrates a specific kind of brilliance, one that sees a fundamental force of nature and asks how it can be weaponized. It represents the ultimate application of pure mathematics and physics to a dire, real-world problem. Whether myth or historical fact, the heat ray forces a fascinating question. If the greatest mind of antiquity could conceive of such a device, what other impossibly advanced ideas were lost when Archimedes himself fell to a Roman soldier's sword, his final diagrams wiped from the dusty ground? His death marked the end of an era of explosive innovation, but the pursuit of perfect, unbreakable protection was just beginning. A wooden disc found in a Greenland fjord holds the secret to Viking mastery of the sea. Unearthed at an abandoned Norse convent, the Unatok disc is a fractured piece of history, its surface etched with lines and a central hole where a gnomon, a small pin, would have been placed. This was no simple sundial. It was a sophisticated solar compass, a navigational computer carved from wood. On the open ocean, under the endless summer sun of the northern latitudes, a Viking navigator would align this disc to the horizon. The shadow cast by the gnomon would trace a path across the carefully inscribed curves, not just indicating the time of day, but revealing true north with stunning accuracy. The genius lies in those carved lines. They are not random scratches. They are a permanent record of the sun's shadow at specific times, a fixed guide calibrated for the unique conditions of the midnight sun. By combining this tool with their deep knowledge of the sun's height, what they called a sun shadow board, a skilled navigator could even estimate their latitude, knowing how far north or south they had traveled. Imagine the trust they placed in this simple piece of wood. With it, they could sail from Norway to Greenland, a weeks-long journey across some of the most treacherous and featureless waters on Earth, guided solely by the sun's arc and a few marks on a disk. This was not magic. It was applied astronomy of the highest order, a system of wayfinding so effective it built trade routes and settled continents. The Vikings did not need complex machinery because they had internalized the cosmos, turning natural phenomena into a reliable map. Their greatest machine was not the disk itself, but the mind of the navigator who knew how to read it. This intimate relationship between human intuition and mechanical aid stands in stark contrast to another ancient navigator's tool, one of such staggering complexity it should not exist. But the sheer hardness of the stone they worked with makes their precision even more baffling. Deep within the granite sarcophagi of the Giza Plateau, there is evidence of a technology that should not exist. The ancient Egyptians drilled holes through solid granite, one of the toughest stones on Earth, with a perfection that defies simple explanation. These are not crude, jagged bores. The holes are perfectly circular, with smooth, parallel sides that show a consistent and precise spiral groove cut deep into the rock. The real shock comes from the core samples sometimes left behind. These slender cylinders of granite, extracted from the center of the drill hole, also bear the same precise, even spiraling. This tells us something incredible. Whatever drill they used did not simply pound and crush its way through. It cut through the granite with a consistent, controlled feed rate, removing material evenly and efficiently, just like a modern diamond-tipped drill bit. The most accepted theory is that they used a tubular drill, a hollow copper shaft, and a generous amount of a loose abrasive like quartz sand. As the drill was turned, the hard sand particles would become embedded in the softer copper, creating a cutting edge that could slowly grind through the granite. But this theory, while logical, runs into serious practical problems. To achieve the feed rate and the deep, clean cuts we see, the drill would have needed to operate under immense, consistent pressure. Some calculations suggest it would require a force of over 2 tons, and then there is the speed. The clean, continuous spiral grooves indicate a remarkably steady and rapid rotation, with almost no wobble or variation. How did they achieve this? Did they have a mechanical means of applying such massive, even pressure? Was the drill shaft mounted in a fixed, stable frame? And what was the power source? Teams of men with a bow drill simply cannot provide the sustained torque and speed needed for such a deep, clean cut in granite. The absence of any wear marks or tool slippage suggests a level of machine stability that we associate with modern, motorized equipment. This is not a case of simple hand tools. This points to a sophisticated understanding of mechanics, leverage, and material science that we have not yet fully credited to the ancient Egyptians. They possessed what appears to be a lost industrial technology, a method for machining hard stone with a level of precision we would struggle to replicate without powerful engines. It forces us to reconsider the very nature of their workshops. Were they filled with the hum of advanced, powered machinery that has since turned to dust, leaving behind only their flawless work in stone as the only testament to their genius? This quest for perfection in hard materials finds a parallel in a civilization that mastered a different element, creating a metal so legendary its recipe remains a mystery. This relentless drive to move immense weight connects directly to the most visible symbol of Roman engineering might. To walk through the Roman Forum or stand before the Colosseum is to be dwarfed by stone, to feel the sheer mass of history pressing down. The question is not just how they designed these structures, but how they physically built them. The answer was a machine of raw power and elegant simplicity, one that transformed the skyline of the ancient world, the Roman treadwheel crane. Unlike the secretive formulas of Greek fire, the Roman crane was a public spectacle, a symphony of coordinated labor and mechanics operating in plain sight. Its power source was not steam or electricity, but human and animal strength, harnessed with breathtaking efficiency. At its heart was a massive wooden wheel, often several meters in diameter, functioning like a giant hamster wheel. Inside this wheel, teams of men would walk forward, their collective steps rotating the axle at the center. This axle was connected to a rope wound around a drum. As the men walked, the rope would spool in, lifting a load attached to the other end through a system of pulleys, and this is where the true genius revealed itself. The Romans had mastered the mechanical advantage of the compound pulley, a system of multiple wheels that dramatically multiplies the force applied. A single man might only be able to lift 50 kilograms directly. But through a sophisticated arrangement of pulleys known as apolispastos, that same man walking inside the treadwheel could help lift several tons. The crane did not just provide muscle, it provided leveraged, controlled, and directed power. The coordination required was immense. A foreman would likely have directed the crew, his voice calling out a rhythm for the men to step in unison, to start, to stop, to hold the load steady as it was precisely positioned. One misstep could send a multi-ton block of stone swinging out of control. Yet they built with a speed and precision that is staggering even today. The Colosseum, for instance, was completed in just under 8 years. They did this without detailed blueprints as we know them. Instead, they relied on standardized modules, precise measurement systems, and the embodied knowledge of master builders who understood proportions, stress, and mechanics intuitively. They passed this knowledge down through apprenticeships, not on parchment. The machines themselves were made of wood and rope, materials that rot and decay. They left behind no intact examples, only hints in stone reliefs and brief mentions in the writings of architects like Vitruvius. Modern engineers have had to reverse engineer these cranes from these fragments, building working replicas that confirm their astonishing capabilities. These reconstructions are a testament to a different kind of mystery. It is not a mystery of a forgotten secret, but of a forgotten scale of execution. We understand the physics, but we struggle to comprehend the sheer logistical audacity. How did they manage the fatigue, the safety, the sheer number of men required to lift every single stone into place? The Roman crane was more than a tool. It was the physical manifestation of an empire's will, a machine that turned human effort into enduring monuments. It proves that advanced technology is not always about hidden gears or lost chemicals. Sometimes it is about organizing brute force with brilliant elegance. And this mastery over weight and leverage found its ultimate expression not in lifting stones, but in a machine designed to lift the human spirit straight into the heavens. Standing in a quiet courtyard in Delhi, a 7-meter-tall iron pillar has defied nature itself for over 1,600 years. While modern steel structures rust and crumble within decades, this ancient column remains as smooth and uncorroded as the day it was forged. It is a testament to a metallurgical secret so advanced it would not be rediscovered until the 20th century. The pillar is not made of some mysterious alloy, but of surprisingly pure wrought iron. Its resilience lies in a delicate, accidental shield known as a passive protective film. Ancient Indian smiths, working without any knowledge of modern chemistry, crafted the iron with a high phosphorus content and very low sulfur and manganese. As the metal cooled, this specific recipe encouraged the formation of a thin, invisible layer of iron hydrogen phosphate that adheres to the surface, blocking oxygen and moisture from ever reaching the pure metal beneath. This was not a coating that could wear off. It is an integral part of the metal's skin, a self-healing barrier that has protected it for centuries. The mystery deepens when we consider how they made it. Creating a single, solid piece of wrought iron of this size and purity is a staggering feat. Modern blast furnaces produce molten iron, but ancient furnaces could not reach such high temperatures. Instead, they likely used a technique called forge welding. They would have heated small pieces of iron in a charcoal furnace, hammering them together on an anvil while white-hot to fuse them into a single, massive bloom. This pillar is the result of countless such cycles, an object painstakingly built by hand, layer by layer, until it reached its monumental size. The uniformity of its composition is what truly astounds metallurgists. How did they maintain such consistent phosphorus levels throughout this arduous, days-long process? How did they achieve such perfect welding without introducing flaws or weaknesses that would have caused the pillar to crack under its own weight over the centuries? They possessed an embodied knowledge, a feel for the metal that was passed down through generations of masters, a science that was practiced rather than written. This was not a secret formula written on a scroll. It was a secret process lived in the rhythm of the hammer and the heat of the forge. We can analyze the pillar and understand why it does not rust, but we cannot fully replicate the lost art of the hands that made it. It stands not just as a monument to a king, but to the anonymous smiths whose genius was so complete it literally became part of the element itself. But the greatest sounds of the ancient world were not born from fire or force, but from the elegant marriage of water and air. In the bustling city of Alexandria, an inventor named Ctesibius turned his genius from weapons to wonder, creating an instrument that would fill vast amphitheaters with a sound never before heard. He called it the Hydraulis, the water organ. Its principle was a stroke of pneumatic genius. A complex pump, often worked by a team of slaves, forced air into a large, submerged chamber called a penegius. This chamber sat within a larger tank of water, which acted as a perfect pressure regulator. As the air entered, it displaced the water, creating a reservoir of compressed air that was held at a constant, steady pressure by the weight of the water itself. This solved the most fundamental problem of wind instruments, the uneven breath of a human player. Here, the air supply was unwavering. This stable air was then channeled to a row of pipes, but the true revolution was the control mechanism. The musician sat before a series of sliders, the world's first keyboard. By pressing one, they would open a valve, allowing that perfectly pressurized air to flow into a specific pipe and produce a single, clear, and sustained note. For the first time in history, a single performer could command an entire orchestra of sound, playing complex melodies and rich, thunderous chords that could hold an audience of thousands spellbound. The complexity of its design is staggering. It was a machine of precision valves, airtight seals, and balanced hydraulics, a system that would not look out of place in an early industrial factory. How did they craft such airtight pistons and perfectly fitted valves without modern lathes or standardized tools? Each component had to be hand-fitted by master craftsmen, their understanding of pneumatics and hydraulics so advanced they could translate theory into breathtaking musical reality. The Hydraulis was not a primitive prototype. It was a fully realized masterpiece that remained popular for centuries, a centerpiece of Roman games and Greek theaters. Its legacy echoes in every cathedral pipe organ and every piano concerto, a direct line back to that first keyboard pressed in Alexandria. It proves that ancient innovation was not solely for war or work, but also for the pure, sublime joy of creating something beautiful. And sometimes the most advanced machine is the one designed not to conquer but to captivate. High on a mist-shrouded Andean peak, the stones of Machu Picchu do not simply sit atop one another, they embrace. They are a colossal, three-dimensional puzzle carved from granite, each block uniquely shaped to interlock with its neighbors in a way that defies logic and has defied earthquakes for over 500 years. This is not simple stacking, this is stone knitting. The precision is so absolute that you cannot slide a single piece of paper between the seams. The angles are complex, with some blocks featuring more than 30 distinct facets, all cut to perfection. How did the Inca, working without iron tools, without the wheel, and without a written system of plans or numbers, achieve this? The conventional explanation points to simple stone hammers and patient abrasion with sand and water. But the scale and the perfection force us to ask if that is the whole story. To shape a single massive block in this manner using only pounding stones would be a lifetime's work for one person. Yet here there are thousands of such blocks fitted together into a sprawling city. Did they possess a lost technique, perhaps a plant-based solvent that could temporarily soften the hard granite, allowing them to mold it like clay? Or does the answer lie in a form of advanced template technology? Perhaps they used precise clay molds that would harden around a protrusion of one stone, creating a perfect negative impression. This mold could then be carried to the next block, guiding the stonemasons exactly where to chip and grind to achieve that flawless fit. This method would explain the incredible variety of shapes, as each stone was custom fitted to its specific place in the wall. The result is a structure with unparalleled resilience. During an earthquake, a modern mortar-based wall is rigid. It cracks and collapses, but an Inca wall is designed to dance. The interlocking stones and the subtle flexibility of their dry joints allow the entire structure to shift and settle during a tremor, and then settle perfectly back into place once the shaking stops. Their engineering understood dynamism, not just static weight. This was a living architecture, a conversation with the mountain itself. The true machine here was not a tool, but a system, a process of creation so refined it turned rock into fabric. It stands as a silent challenge, a question carved in stone about what we consider primitive and what we deem advanced. But the most profound cooling systems required no moving parts at all. In the scorching deserts of ancient Persia, architects designed a machine made of sky and stone, a structure that could turn the blistering wind into a refreshing breeze. These were the Windcatchers, towering sentinels of cool air rising from the rooftops of cities like Yazd. Their design is a masterpiece of passive climate control, a brilliant application of physics carved from mud brick. A windcatcher is essentially a tall, chimney-like tower open at the top, rising high above a building to capture the fastest, coolest currents of air. But the true genius lies in its internal journey. The captured wind is funneled down the shaft, descending into the heart of the home. There, it often passes over a pool of cold water or through the cool, subterranean layers of the earth itself, chilling the air through evaporation and conduction. Meanwhile, the hot, stale air inside the building is drawn up and out through a separate channel, creating a continuous, self-sustaining cycle of ventilation. This was not guesswork. It was a sophisticated understanding of fluid dynamics and pressure differentials, principles we would not formally name for centuries. The builders knew that hot air rises and that drawing it out would pull cooler air in. They oriented each tower with pinpoint accuracy to align with the prevailing seasonal winds, and they shaped the internal channels to maximize airflow without turbulence. Modern engineers trying to replicate these systems often discover that a miscalculation of just a few degrees in orientation, or the wrong internal surface material, can render the entire structure ineffective. The ancient builders possessed an intimate, localized knowledge that was passed down through generations, a science of place and material that we have largely lost. They did not fight their environment, they collaborated with it, using the desert's own elements to conquer the desert's heat. In an age of massive energy consumption, these silent, elegant towers stand as a powerful inspiration for sustainable architecture, proving that the most advanced technology is sometimes the one that works in perfect, quiet harmony with nature. This quest to master the environment leads us to a machine that did the opposite, creating a world of artificial winter in the heart of summer. Deep in the jungles of the Yucatan, a stone tower rises above the canopy, its design unlike any other Mayan structure. El Caracol, named for its interior spiral staircase, is not a temple or a palace. It is an observatory, a machine of stone and shadow built to track the heavens. Its narrow, tube-like windows are not placed at random. Each one is a precise sightline, carefully aligned to frame the exact point on the horizon where Venus would first appear as the evening star after a long period of invisibility. Other slots captured the solstice sunsets or the extreme movements of the moon. This was not architecture for worship alone, it was a scientific instrument of breathtaking ambition. The Maya did not just watch the sky, they measured it with a mathematician's cold precision. They calculated the solar year to be 365.2420 days, a figure more accurate than the calendar used in Europe at the time. They tracked the complex 584-day cycle of Venus with an error of just 1 day every 500 years. They could predict eclipses with terrifying accuracy. But they did all of this without lenses, without telescopes, without any of the optical tools we associate with astronomy. So what was their secret? The observatory itself was the fixed frame, the stable platform. But the moving parts, the precise instruments, were almost certainly made of perishable materials. We believe they used crossed sticks as sighting tools, or perhaps bundles of reeds arranged to create precise angles for measurement. They may have used vessels filled with water as primitive reflecting pools to observe the transit of stars. The real instrument, however, was their system of mathematics. They were one of the first civilizations to conceptualize the number 0, and they used a complex base 20-decimal system that allowed them to perform enormous calculations and record vast cycles of time. Their astronomical tables, recorded in bark paper codices, are filled WITH Chinese letter, 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 that chart the movements of celestial bodies across millions of days. This was not abstract knowledge. It was woven into the very fabric of their culture, dictating the timing of wars, the coronation of kings, and the sacred rituals that sustained their world. A king would not launch a campaign unless Venus was in a favorable position. They did not see a separation between the science of the stars and the spirituality of their existence. The cosmos was a grand, mechanical, and predictable clock, and by understanding its gears, they believed they could influence its outcome. The mystery is not just what tools they held in their hands, but what they held in their minds. How did they achieve such a profound synthesis of calculation and belief? Their silent stone observatories stand as a monument to a lost science, one that saw the universe as a single, interconnected machine where human destiny was written in the stars. Yet for all their mathematical precision, the Maya could not forge metal. That art belonged to the smiths of Damascus, who created a material so legendary its name is still whispered with reverence. The steel they produced was not merely strong, it was a paradox given form. A blade forged from this metal could be sharp enough to split a falling silk scarf in midair, yet flexible enough to bend nearly double without snapping. It was resilient, resisting the nicks and chips that would shatter lesser swords, and it was beautiful, its surface marked by a distinctive, wavy pattern that looked like flowing water or wood grain frozen in metal. This was not a single invention, but the pinnacle of a lost art, a perfect marriage of specific materials and a secret process that vanished by the 18th century. The source was a unique type of raw material known as Wootz steel, ingots of ultra-high carbon iron that were imported from India and Sri Lanka. These ingots were the canvas, but the Damascus smiths were the artists. Their method was a symphony of controlled heat and hammer blows, a recipe passed down through generations. They would slowly heat the steel in a small clay furnace, often sealed to control the atmosphere. The carbon within the metal would begin to form microscopic structures, carbide bands that are the source of the legendary strength and that distinctive watery pattern. The true secret, however, lay in the cooling. The temperature had to be brought down with a painstaking, precise slowness, often over many days. This gradual process allowed the carbon to arrange itself into those perfect, resilient patterns. Then the smith would begin to fold and weld the metal, not just to shape it, but to further distribute these carbon bands, laminating the steel into thousands of microscopic layers that gave the blade its impossible flexibility. They worked without pyrometers to measure temperature, without spectrographs to analyze composition. They judged the steel's readiness by the precise color of its glow in the dim forge, a knowledge held in the eye and the hand of the master. They knew the exact sound the hammer should make when it struck the metal at the right temperature. This was a science of sensation and intuition, an embodied knowledge that died with the masters who held it. Modern attempts to recreate Damascus steel often fall short. We can analyze a sliver of an ancient blade under an electron microscope and see the nanostructures, the carbon nanotubes that contributed to its strength. We can replicate the chemical composition almost exactly, but we cannot replicate the centuries of accumulated craft, the subtle, unwritten nuances of the hammer's rhythm and the fire's breath. The mystery is not just what they did, but how they knew. How did they achieve such breathtaking consistency, batch after batch, without a single written formula? The answer lies in the silent language of the workshop, a language we can no longer hear. While Damascus steel was a masterpiece of the forge, another Roman invention shaped the world on a far grander scale. Their concrete did not just build walls, it built an empire that has physically outlasted its own collapse. Walk into the Pantheon in Rome and look up. Your gaze is met by the largest unreinforced concrete dome in history, a perfect hemisphere that has hovered impossibly over the city for nearly 2,000 years. It has weathered earthquakes, invasions, and the relentless pollution of the modern world. It should have crumbled to dust centuries ago. Instead, it stands stronger than the day it was finished, a silent rebuke to our own crumbling infrastructure. The secret is not in a single ingredient, but in a chemical reaction that time itself cannot stop. Roman engineers mixed their concrete with a specific volcanic ash known as pozzolana, mined from the regions around Mount Vesuvius. When this ash was combined with lime and seawater, a miraculous process began. Instead of simply drying, the mixture started a complex chemical conversation. Tiny plate-like crystals of a mineral called stretlingite began to form within the matrix, but the real magic happened over centuries. As minute cracks inevitably formed from stress and settlement, water would seep in. In modern concrete, this is the beginning of the end, as the water rusts steel rebar and expands with frost, widening the cracks. In Roman concrete, that invading water was not a destroyer but a healer. It reacted with the leftover volcanic ash and lime, triggering the growth of new, interlocking crystals that literally filled the cracks from the inside out. The concrete was not just durable, it was self-healing. Modern Portland cement, by contrast, is designed for speed and initial strength, not longevity. The chemical process it undergoes creates brittle, glass-like structures and often produces expansion that leads to its own internal destruction over decades. We build with the assumption that structures are temporary, but the Romans built for eternity. They understood that the true test of a material is not its first year, but its thousandth. The full recipe and mixing process remain elusive. We know the ingredients, but not the precise ratios, the mixing technique, or the curing conditions that turned simple volcanic rock into a stone that grows stronger with age. This was not an accident. It was applied chemistry of the highest order, a deep understanding of material science that we are only now beginning to decode with electron microscopes. What does it say about our own progress when the most advanced building material we have cannot outperform a 2,000-year-old recipe? While the Romans built an empire in stone on the other side of the world, a different kind of machine was navigating the complexities of power and ceremony. In the courts of 3rd century China, a magnificent procession would unfold. At its heart rolled an ornate, human-drawn chariot, and upon it stood a figure with an outstretched arm. No matter how the chariot twisted and turned through the palace grounds, no matter how many corners it took, the figure's finger never wavered. It pointed unerringly towards the south, the cardinal direction of imperial authority. This was the legendary south-pointing chariot, a mechanical marvel that performed a magic trick using nothing but gears and genius. It achieved this impossible feat centuries before the magnetic compass became a common navigational tool in China. The secret was not magnetism, but mathematics carved into bronze. Inside the chariot's housing was a system of differential gears, a concept so advanced it would not be reinvented in the West until the automobile. Here is how it worked. The chariot's wheels were connected to the gear train. When the chariot moved in a straight line, the gears turned in unison, and the figure on top remained perfectly still. But the moment the chariot began to turn, the magic happened. The wheels would rotate at different speeds. This difference was captured by the differential gears, which calculated the precise angle of the turn, and then rotated the figure on top in the exact opposite direction, perfectly cancelling out the chariot's change in heading. The result was a statue that appeared completely independent of the vehicle's motion, a fixed point in a turning world. The sheer sophistication of this mechanical computer is staggering. The Chinese engineers who designed it had to possess a profound understanding of rotational motion and gear ratios. They had to hand-cut each tooth on those bronze gears to a perfection that would allow for minimal friction and absolutely no slippage, as even the tiniest error would accumulate over distance and send the pointer drifting hopelessly off course. They built this without precision lathes, without CD software, without any of the tools we consider essential for such fine mechanical work. Their tools were their brilliance, their patience, and an empirical knowledge of mechanics that was generations ahead of its time. The chariot was likely more than a practical tool. It was a potent symbol of imperial power, a demonstration that the emperor's court could literally master direction and destiny itself. It was a piece of political theater powered by what we would now call robotics, an automaton performing a single, flawless task. It makes you wonder, if they could build this, what other automated machines might have graced those ancient palaces, lost to us because they were made of bronze and wood instead of stone. Yet for all the complex gearwork of the south-pointing chariot, the most brilliant optical machine of the ancient world required no moving parts at all, only a flame and a mirror. Guiding sailors into the great port of Alexandria stood a tower of such immense scale and ingenuity, it defined the very skyline of the ancient world. The Lighthouse of Pharaohs soared over 100 meters into the Mediterranean sky, a staggering white marble colossus that was among the tallest man-made structures on Earth for centuries. It was not merely a tower with a fire on top. It was a carefully engineered instrument of light, a machine designed to project safety across vast, empty distances. By day, its brilliance came from the sun. Ancient accounts describe a massive, polished bronze mirror, likely concave in shape, mounted at the summit. This was not a simple reflective sheet. It was a precision instrument, angled to capture the sun's rays and focus them into a searing, concentrated beam visible for dozens of kilometers out to sea. This daily signal provided a critical navigational fix long before land was even visible. But at night, the machine transformed. The great mirror was now directed towards a colossal furnace burning at its center. A fire fed by a constant supply of wood or resin hauled up the spiral ramp inside the tower by teams of laborers and donkeys. The mirror would then reflect and project this massive firelight, turning a simple flame into a directed, powerful beacon that cut through the darkness and the fog. The true engineering mystery is not the existence of the mirror, but its operation. How did they aim and adjust a multi-ton bronze disc to achieve a precise focal point? Was it mounted on a pivoting frame, operated by a team of keepers using a system of counterweights and pulleys? How did they keep the surface polished and free of salt corrosion in the harsh marine environment? a maintenance task of heroic proportions. The loss of the lighthouse to a series of medieval earthquakes represents more than the fall of a beautiful building. It created a permanent gap in our understanding of ancient optical engineering. We have fragments of texts praising its light, but no technical manuals describing its heart. This was applied science on a monumental scale, a testament to a civilization that understood reflection and refraction well enough to build a machine that touched the horizon. Yet the most dramatic illusions were not for entertainment, but for devotion. Within the sacred confines of an Egyptian temple, a hushed crowd of worshippers would gather. A priest would approach the altar and light the sacred flame. As the fire grew, a low, groaning sound would emanate from the very walls. Then, without a single human hand touching them, the massive, heavy bronze doors of the temple would begin to swing inward, seemingly of their own divine volition. To the faithful, it was a miracle, a direct sign that the gods had accepted their offering and were opening the way for communion. In reality, it was a masterclass in mechanical engineering, designed by the same mind that gave us the steam engine, hero of Alexandria. His system of automatic temple doors was a breathtaking fusion of physics, theater, and psychological insight. The secret lay in a carefully hidden apparatus. Beneath the altar, Hero placed a sealed air vessel. As the fire on the altar grew hotter, it warmed the air inside this vessel. Air expands when heated, and this expanding air had to go somewhere. It was forced through a pipe into a large bucket hidden below the temple floor. The bucket was part of a counterweight system connected by ropes and pulleys to the massive doors. As the expanding air pressurized the bucket, it forced water out of it and into a separate container. The now empty bucket, now lighter, would rise, pulling on the ropes and pulleys. This carefully calibrated action would slowly and majestically open the doors. When the altar fire was extinguished, the process reversed. The air in the vessel cooled and contracted, creating a vacuum that sucked the water back from the container into the bucket. The now heavier bucket would descend, pulling the ropes the other way and swinging the great doors shut. The entire mechanism was a closed hydraulic system, a perfectly balanced loop of cause and effect. The true genius was in the concealment. Every pipe, every pulley, every weight was buried deep within the stone architecture, completely invisible to the awestruck worshippers. The low groaning they heard was not the voice of a god, but the sound of water sloshing through pipes and ropes straining under tension, amplified by the hollow spaces in the walls. Hero understood that the spectacle's power relied entirely on the illusion of magic. He was not just an engineer, he was a master showman who used technology to elevate a spiritual experience. This raises a profound question about the nature of invention itself. Was this a deception or an enhancement? The priests were not merely tricking their congregation. They were using the most advanced technology of their age to make the divine feel tangible, immediate, and real. The machine served belief, proving that the line between technology and magic is often just a matter of visibility. This brutal elegance was built on a simple, yet devastatingly effective principle: torsion. The Roman Ballista was not a simple catapult that relied on the flex of a wooden arm. It was a machine that harnessed the stored energy of twisted sinew. At its heart were two vertical wooden frames, each holding a thick bundle of ropes, often made from animal sinew or women's hair, materials chosen for their incredible elasticity and strength. Through each bundle, a rigid throwing arm was inserted. The real magic began when the crew used a winch to crank the arms backward. This rotation twisted those rope bundles tighter and tighter, storing immense potential energy like a giant, terrifying spring. When the winch was released, the arms snapped forward with blinding speed, propelled by the unwinding torsion of the ropes. slinging a heavy stone or a sharp bolt downrange with terrifying force and pinpoint accuracy. These were not area denial weapons for indiscriminate bombardment. A well-trained ballista crew could hit a specific section of a wall or pick off a key individual at an astonishing distance of several hundred yards, acting as the ancient equivalent of a sniper rifle. The genius of Roman engineering lay in the subtle details we often miss. The composition of the rope bundles was a precise science, a specific blend of materials to achieve the perfect balance of elasticity and recoil. The design of the washer, the key that held the rope bundle in place and allowed for tension adjustment, was a masterpiece of lathe-turned bronze that had to withstand unimaginable forces without shattering. The frame itself was not just wood, but a specific geometry that absorbed the massive shock of release without shaking itself apart. This is where modern reconstructions often fail. We can build a ballista that looks right, but we lack the intimate, generational knowledge of material properties. How dry did the sinew need to be? How exactly was it waxed and treated to prevent rot and maintain its spring? What was the precise rhythm for winding the winch to achieve optimal tension without over-tightening and snapping the ropes? The Romans did not have strain gauges or computers to model stress. Their knowledge was empirical, earned through catastrophic failure and brilliant success on battlefields across the known world. They understood their materials so completely that they could calibrate these massive machines by feel and by eye, achieving a lethal consistency that helped build and secure an empire. This mastery over tension and release, over converting stored energy into targeted destruction, represents a pinnacle of mechanical thought. It forces us to reconsider the very nature of innovation, proving that sometimes the most advanced machine is not the most complex, but the one whose every component is perfected to serve a single, devastating purpose. Descending into Chand Bayori feels like stepping into a different world, a geometric canyon carved from the earth, with over 3,500 perfectly symmetrical steps cascading down 13 stories. It is one of the deepest and largest stepwells in India. But this was far more than a source of water. It was a masterpiece of climate control, an ancient refrigerator built from stone and shadow. In the blistering heat of the Rajasthan desert, these stepwells provided a sanctuary of cool air, a public utility that harnessed basic physics to create a life-saving microclimate. The principle was evaporation. The vast, exposed surface area of the water at the bottom, combined with the sheer depth of the structure, created a natural convection cycle. Hot, dry air at the surface would sink down the steps, cooling as it descended. When it reached the water, it would pick up moisture, becoming cooler and heavier, settling at the lowest levels. This process created a dramatic temperature differential, often as much as 10 to 15 degrees cooler than the scorching air outside. The architectural design was not an accident, it was precise engineering. The steps were arranged to maximize shade throughout the day, ensuring the water and the surrounding stone never absorbed the full force of the sun. The narrow base and wide top of the structure funneled the wind downward, enhancing the natural airflow. But how did they calculate this? Without modern thermodynamics, how did they know the exact depth, the perfect step angle, the ideal surface area of water required to achieve this cooling effect? The answer lies in generations of observation and refined tradition. Builders learned through trial and error, passing down ratios and proportions that worked. They understood their environment so intimately that they could read the land and the wind, designing a structure that worked in perfect harmony with nature. In an era of energy-intensive air conditioning, these silent, beautiful wells stand as a timeless lesson in sustainable design, proving that sometimes the most advanced technology requires no power at all, only a deep and profound understanding of the world around us. But the Vikings navigated by more than just the sun's disk. When the sky turned to a featureless gray blanket and the horizon vanished into mist, their greatest tool may have been a crystal held to the eye. The Norse sagas speak of a solarstein, a sunstone, a magical mineral that could reveal the sun's position even on the cloudiest days. This was not a myth. It was a brilliant application of a subtle property of light, a secret weapon for the worst weather the North Atlantic could conjure. The leading candidate for this legendary stone is a crystal known as Iceland spar, a transparent form of calcite that possesses a unique quality called birefringence. When light passes through it, the crystal splits the light ray into two separate beams. The key to its use is polarization. Sunlight becomes polarized as it scatters through the atmosphere, meaning its waves vibrate in a specific direction relative to the sun's position. By holding the Iceland spar up to the sky and rotating it slowly, a Viking navigator would watch for a change. At a certain angle, one of the two images within the crystal would appear darker while the other remained bright. The point where the two images matched in brightness indicated the direction of the polarized light, and thus the hidden sun. It was a celestial compass locked inside a rock. The sheer practicality of this on a heaving longship is what defies belief. How did they steady their hand enough to read the subtle shift in light while standing on a wet deck being tossed by waves? How did they calibrate such a delicate instrument without any formal understanding of optical physics? They must have developed a profound tactile intuition, a feel for the crystal and the light that could only be learned through years of experience on the open ocean. The absence of a definitive archaeological find is the final layer of the mystery. We have no sunstone recovered from a Viking grave clutched in the hand of a navigator king. We have only the tantalizing mentions in their stories and the cold, hard science that proves it would have worked. This device is the ultimate symbol of Viking ingenuity. It represents a mindset that refused to be limited by the environment. If the sky would not show them the sun, they would find a way to pull its direction from the empty gray air itself, turning a simple crystal into a window to the heavens. Yet the most vital machines are often the ones we never see, hidden beneath our feet. Deep within the labyrinthine palace of Knossos, the true marvel is not the grand courtyards or the vivid frescoes, but what flows silently within its walls. Over 3,000 years before the Common Era, the Minoans engineered a plumbing network of breathtaking sophistication, a secret circulatory system that gave life to the very stone. They crafted terracotta pipes with a unique tapered design, each section narrowing at one end to fit snugly into the next, creating a perfect watertight seal. These were not merely laid in a ditch, they were installed with a precise, calculated gradient, ensuring a constant and efficient flow of fresh water into the palace from mountain springs miles away, while waste was just as efficiently carried out through a separate, dedicated drainage system. This was not a crude attempt, it was a masterclass in hydraulic engineering and urban planning. They understood the principles of gravity and pressure, of preventing backflow and stagnation, concepts that would be forgotten and then rediscovered millennia later. How did they achieve such seamless seals without modern rubber or welding? They used a natural cement made from lime and clay, creating a bond so strong it has survived earthquakes and millennia of neglect. This was more than convenience, it was public health on a monumental scale, a society that valued sanitation and comfort, that understood the direct link between clean water and a thriving community. To stand in those ruins is to witness a quiet revolution. While other contemporary cultures were drawing water from muddy rivers, the Minoans were enjoying a steady, pressurized supply within their own homes. Their genius was not in a single dramatic machine, but in the elegant, invisible network that sustained daily life, a hidden architecture of wellness that challenges our perception of ancient civilization itself. What unites these 24 marvels is not just their mystery, but a shared brilliance in the face of limitation. Each one represents a profound conversation between the human mind and the natural world. They did not fight their environment, they collaborated with it, using the fundamental forces of physics leverage hydraulics, optics, and chemistry as their building blocks. They saw the sun not just as a light source but as a weapon. They understood water not just for drinking but for powering music and creating coolness. They looked at a simple crystal and saw a compass hidden within its heart. This was not magic, it was applied genius, a deep, intuitive science born from relentless observation. Their innovation was also born from necessity, but a necessity defined by their time. The purpose of these machines was almost always one of three things: survival, supremacy, or the spirit. They were built to win wars, to grow food, to navigate treacherous seas, to honor gods, or to awe the faithful. The Roman Ballista secured an empire. The Minoan plumbing sustained a city. Zhang Heng's Seismoscope saved lives. The Antikythera Mechanism and the Mayan Observatory sought to understand humanity's place in the cosmos. Every invention served a direct, vital role in the fabric of their society, which is precisely why they were pursued with such incredible passion and skill. And this is the most humbling lesson they offer us. Their irreplaceability today does not stem from a lack of ancient skill, but from our own loss of their embodied knowledge. We have the formulas, the blueprints, the electron microscopes. What we lack is the master smith's feel for the hammer and the heat of the forge that created Damascus steel. We lack the navigator's innate sense of how to hold a sunstone on a storm-tossed deck. We lack the collective, unwritten wisdom passed down through generations of stonemasons who knew how to make granite blocks embrace. This was knowledge held in the hands, the eyes, and the soul, not in a manual. When those lineages were broken by war, famine, or simply the passage of time, that knowledge vanished forever. This forces a radical rethinking of history itself. We often view technology as a straight line, always climbing upward from primitive to advanced. But these machines tell a different story, one of peaks and valleys. The ancient Greeks built a precision-geared computer, and then that knowledge disappeared for over a millennium. The Romans formulated a self-healing concrete that we still cannot perfectly replicate. They reached dizzying heights of sophistication in specific areas, only for that expertise to be forgotten, forcing later civilizations to rediscover the same principles centuries later. Progress is not a guaranteed ascent. It is a fragile thing that can be lost. Perhaps the greatest takeaway from these 24 mysteries is a call for humility and preservation. They encourage us to value not just the end product of innovation, but the interdisciplinary process that creates it, the blend of art, science, and craft. They remind us that the most advanced solution is sometimes the simplest and most sustainable, like the Persian Windcatcher or the Indian Stepwell. And they urge us to protect our own knowledge, not just in digital clouds, but in the hands of skilled artisans and the hearts of curious minds. For the greatest machine we risk losing is not made of gears or stone, but of the collective human genius that built them, a spark that must be tirelessly nurtured and passed on, lest it too flicker and fade into the shadows of time. From the intricate gears of the Antikythera Mechanism to the flowing water of Minoan plumbing, these 24 mysterious machines reveal a profound truth about our past. They are not mere anomalies or lucky accidents, but brilliant testaments to the limitless curiosity of ancient civilizations. Each one stands as a powerful reminder that our history is not a simple, complete story. but a tapestry woven with gaps and wonders, many of which are still waiting patiently to be rediscovered. As we continue our own relentless march of technological advancement, let these artifacts inspire more than just historical interest. Let them inspire a deep sense of humility, a genuine awe for what was achieved with so little, and a renewed respect for the raw power of the human mind when it is driven by necessity and wonder. The journey does not end here. The past is filled with countless other enigmas just waiting to be unraveled. Thank you for joining this exploration into history's greatest machines. If you enjoyed this deep dive, subscribe for more journeys into the unknown, and let us know in the comments below which of these impossible inventions fascinates you the most.